In this video, we have a second-order linear homogeneous equation of the form a times y double prime plus b times y prime plus c y equal to 0. And here we have the indicial equation am squared plus bm plus c equal to 0. And the indicial uh, equation has complex roots of the form alpha plus minus beta I. And so as an example, uh, here we have the second order linear homogeneous equation y double prime minus 6y prime plus 13y equal to 0. And so the characteristic or the indicial equation is m squared minus 6m plus 13 equal to 0. And the roots of the indicial equation will be 3 plus or minus 2i. So in this case, alpha will be 3 and beta will be 2. And next, I'm going to set m1, which is root 1, is 3 plus 2i. And then m2 will be 3 minus 2i. Because 3 plus minus 2i, they are the roots. And if we plug them back into the indicial equation right here, it will get 0, meaning 3 plus 2i squared minus 6 times 3 plus 2i plus 13 is 0. And 3 minus 2i squared minus 6 times 3 minus 2i plus 13 is also 0. And next, I will show that the function y sub 1 equal to e to the m1x, or in this case, it will be e to the 3 plus 2ix, is a solution of the linear homogeneous differential equation here. And so let's take the first derivative and the second derivative and then plug them into the differential equation and verify that it's equal to 0. So this is the first derivative. This is the second derivative. Now replace y double prime with the second derivative here and replace y prime with the first derivative. And then we can see that the common factor is e to the 3 plus 2ix. And then this expression right here, which is this, it is equal to 0. And therefore the function y1 equal to e to the 3 plus 2ix is a solution of this linear homogeneous differential equation. And similarly, the function y equal to e to the 3 minus 2ix is also a solution of the linear homogeneous differential equation here. And so in general, for the second order linear homogeneous differential equation, ay double prime plus by prime plus cy equal to 0. And if the roots of the indicial equation are complex numbers like alpha plus minus beta I, then the functions e to the alpha plus beta ix and e to the alpha minus beta ix, they are solutions of the differential equation. And so recall that if two functions, y1 and y2, if they solutions of the second order linear homogeneous differential equation here, and then any linear combination of these two functions here is also a solution. And so in this example, we have e to the 3 plus 2ix is a solution, e to the 3 minus 2ix is a solution. And therefore, any linear combination of these two functions right here will be a solution. For example, this linear combination is a solution. This linear combination is a solution. The linear combination of 0.5 e to the 3 plus 2ix plus e to the 3 minus 2ix, this linear combination is a solution of this differential equation. It's always negative 0.5I times e to the 3 plus 2ix minus e to the 3 minus 2ix is also a solution of this differential equation. And then we can verify that this linear combination is a solution. We can take the first derivative, the second derivative, and then plug them in here into the differential equation here, and then show that it's equal to 0. And so once again, these linear combinations right here, they are solutions of the differential equation. And next, what I like to show is that the function e to the alpha x cosine beta x and the function e to the alpha x and sine beta x here, they are solutions of this linear homogeneous differential equation. And recall that the power series for e to the z here is 1 plus z squared over 2 factorial and so on. And then the power series for cosine of z is 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial and so on. And then this is the power series representation for sine of z. And therefore, e to the iz, the imaginary I, and then times z would be 1 plus iz squared over 2 factorial and so on. And then simplify here, we get 1 plus iz plus I squared times z squared over 2 factorial and so on. And recall that I squared is negative 1, I to the third is negative I to the fourth is 1, and so on. And so right here we get negative 1, I to the third we get negative I to the fourth we get 1, and so on. And then separating the even powers and the odd powers, then we get two expressions like this. This is cosine of z, and this is sine of z. So e to the iz is cosine of z plus I times sine of z. And so we have e to the beta IX, then we'll get cosine of beta x plus I times sine of beta x. And if we have e to the negative beta IX, then it'll be cosine negative beta x plus I sine negative beta x. But recall that cosine is an even function, and so cosine of negative beta x is just cosine of beta x. And then sine is an odd function, and so sine of negative beta x is going to be negative sine of beta x. And so e to the beta IX plus e to the negative beta IX, it will be this expression plus this expression. And then this term And this term here will drop out, and we have 2 cosine beta x. Instead of adding, now we're subtracting. Then it's going to be this expression minus this expression. The cosine beta x here will drop out. What's left is 2I sine beta x. And now let's take a look at the expression e to the alpha plus beta x plus e to the alpha minus beta ix. The first expression right here, this is the same as e to the alpha x times e to the beta ix. And then the second part here, this is e to the alpha x times e to the negative beta ix. Common factor is e to the alpha x times e to the beta ix plus e to the negative beta ix. But this expression here, which is this, so we'll replace this with 2 cosine beta x. So we end up with 2e to the alpha x cosine beta x dividing by 2, we get e to the alpha x cosine beta x is equal to 0.5 e to the alpha plus beta ix plus e to the alpha minus beta ix. And as pointed out a few minutes ago, this is a solution of the linear homogeneous differential equation. And therefore, e to the alpha x times cosine beta x is a solution of the linear homogeneous differential equation. And now let's look at, instead of the sum here, let's look at the difference here. This expression is e to the alpha x times e to the beta ix. And then this part here will be e to the alpha x times e to the negative beta ix. Common factor e to the alpha x times e to the beta ix minus e to the negative beta ix. This expression right here is 2I sine beta x. So we'll replace this expression here with 2I sine beta x, and we'll get 2e to the alpha x times I sine beta x. Divide by 2I, divide by 2I, then we get e to the alpha x sine beta x is negative 0.5i, dividing by 2i, and we get negative 0.5i. And then times e to the alpha beta ix plus e to the alpha minus beta ix. And as shown a few minutes ago, this linear combination here is a solution of the linear homogeneous differential equation. Therefore, e to the alpha x sine beta x here is a solution of this linear homogeneous differential equation. And therefore, we have just shown that e to the alpha x cosine beta x and e to the alpha x sine beta x, they are solutions of this differential equation. Next, we need to show that these two functions here, they are linearly independent so that we can use them to form the basis for the solution space of this differential equation. So the Wronskian determinant of the these two functions here. And then here are the two functions, and then here are the derivative of the two functions. Cross, multiply, and subtract. And then we will end up with beta e to the 2 alpha x. And from the beginning, we made the assumption that the indicial equation has complex solutions, and so beta cannot be 0. And so beta is not 0, and then beta e to the alpha x here cannot be 0. And therefore, these two functions here, they are linearly independent. And therefore, we've just shown that these two functions here, they are solutions of this linear homogeneous differential equation, and they are linearly independent. Therefore, they form the basis for the solution space of this linear homogeneous differential equation. And therefore, any solution of this differential equation can be written as a linear combination of these two functions. And so what that means is that the general solution of the linear homogeneous differential equation here, it will be y equal to e to the alpha x times constant c1 times cosine beta x plus constant c2 times sine beta x. And then for the example, y double prime minus 6y prime plus 13y, recall that the indicial equation is m squared minus 6m plus 13 equal to 0, and the roots are 3 plus minus 2i. And therefore, the general solution will be y equal to some constant c1 times e to the 3x, which is 3 right here, times cosine 2x plus constant c2 times e to the 3x times sine 2x. And that's the end of the video.